Have you ever stopped to think about what connects the polish on your furniture, the sugar in your morning chai, and even the perfume you might be wearing right now? It sounds random, right? Well, today we're going to dive into the hidden chemistry that links them all. We're talking about three incredible families of organic compounds: alcohols, phenols, and ethers. So let's jump right in.
So I know it sounds a bit like a riddle, but just think about it for a moment. You've got the spirit that makes wood shine, the sweetness in your cup of tea, the actual paper in a book, and the delicate scent of a perfume. What on earth could be the chemical thread that ties all of these things together?
And the answer is, it's all down to these three fundamental families of organic compounds. Yeah, all those incredibly different things are built from, or at least with the help of, alcohols, phenols, and ethers. You could say they're kind of the unsung heroes of our everyday chemistry, and we're about to find out exactly why.
Okay, so here's our game plan. We'll start with some real-world examples, then meet the hydroxyl compounds themselves. We'll look at how they're classified, how they behave, and then we'll introduce the ethers. Finally, we'll wrap it all up with the most important takeaways. Let's go.
All right, first stop, chemistry in plain sight. We're going to see just how deeply these compounds are woven into our world, often without us even realizing it.
And their versatility is really the key here. For instance, the spirit used for polishing furniture, that's an alcohol called ethanol. The antiseptics that we use to keep things clean, they're based on phenols. And those beautiful fragrances and perfumes, you guessed it, they often have ethers. What's even more amazing is that things like sugar, cotton, and paper are all made of molecules that share a core feature, that little hydroxyl group, you know, the OH.
So that hydroxyl group is a perfect lead into our next section, where we meet the hydroxyl compounds, alcohols, and phenols. Now, they both share that minus OH group, right? But believe me, where that group is attached, well, it changes everything. So first up, let's talk about alcohols. What makes something an alcohol in the world of chemistry? It's pretty simple, actually. It's when you have one or more of those OH groups attached directly to what we call an aliphatic system. Now, don't let the fancy word scare you. Just think of it as a straight or branched chain of carbon atoms. It's like the basic skeleton of the molecule. Okay, now, what about phenols? Well, they also have that star player, the OH group. But, and this is the big difference, it's attached directly to an aromatic system. An aromatic system is just a fancy way of saying a very stable, flat ring of carbon atoms. And just by changing the neighborhood of that OH group from a chain to a ring, you completely change how the whole compound acts.
And this comparison makes it super clear. On one side, you've got alcohols. Think of them as carbon chains. On the other side, phenols, think carbon rings. It's the exact same functional group, that OH, but its address, its location, is what defines which family it belongs to. It's a really simple rule, but honestly, it's the foundation for everything else we're going to talk about.
So now that we've met the two main families, let's bring some order to the chaos, shall we? We need a system of classification. Think of it like building out the family tree for alcohols, which helps us understand them way better. And the easiest way to start classifying them is literally just to count the OH groups. Super straightforward. If there's one OH group, it's called monohydric. Got two? That's dihydric. Three is trihydric. And if there are a whole bunch of them, we just call it polyhydric. See? Totally logical. But we can go deeper, because monohydric alcohols, the ones with just a single OH group, are so incredibly common, there's another level to how we classify them. This time, it's all about zooming in on the specific carbon atom that's holding on to that hydroxyl group. And that brings us to the three main branches. We call them primary, secondary, and tertiary alcohols. It all comes down to the carbon that's attached to the OH group. Okay, so look at that carbon. Is it bonded to only one other carbon atom? Then it's a primary alcohol. Is it bonded to two other carbons? That makes it secondary. And if it's holding on to three other carbons, you've got a tertiary alcohol. And this isn't just for fun. This little detail totally dictates how it's going to react later on.
Okay, so you might be thinking, why do we care about all this classification? Well, it's because that structure, that family tree, tells us exactly how these compounds are going to behave. So now let's get into their properties and some key reactions.
So here's a curious thing about alcohols. If you put an alcohol next to a similar-sized molecule, like a hydrocarbon, you'll notice two things. The alcohol has a much higher boiling point, and it usually dissolves in water. Why is that? What's the secret sauce here?
The answer is something called intermolecular hydrogen bonding. And I love this analogy. Think of these bonds like social connections between the molecules. The slightly positive hydrogen on one molecule is attracted to the slightly negative oxygen on its neighbor. These little connections act like glue, holding them all together.
That's why you need a lot more energy, a higher temperature, to pull them apart and make them boil. And this sociable nature is also why they love to mix and bond with water molecules, which makes them soluble.
All right, let's switch gears to a classic reaction for phenols. It's called Kolbe's reaction, and it's a fantastic example of chemical transformation. So what happens? First, you treat phenol with sodium hydroxide, which makes it super reactive. Then, this supercharged ion reacts with carbon dioxide. And the result? You get a product called orthohydroxybenzoic acid. Now, why is this cool? Because that is the starting material for making aspirin. It's just a perfect example of how we can take a relatively simple compound and turn it into something that can literally save lives.
Okay, we've tackled alcohols and phenols. It's time to meet the final member of our trio, the ethers. Now, these guys also have oxygen in them, but it's arranged in a totally different way.
So how do you make an ether? Well, imagine you take an alcohol or a phenol. You find that OH group, and you swap out the hydrogen for another group that has carbon in it, what we call an alkylar aryl group. What you're left with is this really cool structure where an oxygen atom is like a bridge connecting two groups on either side. We write it out as ROR.
And classifying ethers is super easy. You just look at the two groups on either side of that oxygen bridge. Are they the same? If yes, it's a symmetrical ether. Are they different? Then it's an unsymmetrical ether. That's it. Simple, right?
Wow, okay. So we've gone from furniture polish all the way down to molecular structures and reactions. Now let's pull it all together and recap the main points from our tour.
So, what are the big takeaways here? First, everything about alcohols, phenols, and ethers comes down to their functional groups, that -OH or the ROR bridge. Second, remember the core difference. For an alcohol, the OH is on a chain. For a phenol, it's on a ring. And that changes everything. Third, we learned that classification is our friend. It helps us predict how these compounds will behave. We also saw how those social connections from hydrogen bonding give alcohols their high boiling points. But most importantly, I hope you see that these aren't just things in a textbook. They are literally the building blocks for so many products we use every single day.
And this quote really brings us full circle, doesn't it? Right back to where we started. That ordinary spirit for polishing furniture, it's not some magic potion. It's just ethanol, a simple alcohol with a hydroxyl group. It's the perfect reminder that this amazing chemistry is all around us, hiding in plain sight. So, I'll leave you with this one last thought to chew on. We've seen alcohols as solvents, phenols as antiseptics, and ethers in perfumes. Each one is obviously super important. But if you absolutely had to pick one, which family of compounds do you think is the most vital to our modern lives? It's a tough one, right? But it's definitely something to think about.
Thanks so much for joining me.